Hello everyone in Gather. I've started the next live stream, so please put yourself in quiet mode and mute yourself and head over to one of the TVs or the YouTube channel. I've also posted the link to the current YouTube stream in the Gather chat and on Discord and on Slack. Just make sure you find it, and we'll see you over there. All right, I'm just going to wait a tiny bit more for everyone to join from Gather. This is our second session of the day on Sunday. Today we're going to hear from me and from Matthew, both about attempts to come up with new syntaxes for the Rhombus project. And for my talk, it'll be, I previously recorded it like the other talks we've had earlier, and we'll do questions afterwards, the same way that we've done questions so far. You can put them in the Google document that you can see on the text podiums. And for Matthew's talk, we're going to do it a little bit differently, where you can ask questions as we go. And so I'll be monitoring the Google Doc and on Gather and on YouTube, and I'll interrupt Matthew. And Matthew will also have those open and on another screen, and he'll notice as well. I can see now that we have a pretty stable set of people watching. So I'm going to turn on the next talk, and we'll go from there. Let me turn off my sound and video.
I'm going to be talking today about C-exprs and Lexburs, or C-exprs and Lexburs. Here's a little example S-expression program that I pulled from one of the Racket guides. And when I look at this, part of me sees something really beautiful, which is that S-expressions have a very regular structure, and that regular structure makes them sort of, quote, trivial to parse, meaning that since it's all the same thing everywhere, it's very easy to parse and manipulate. There's this very simple tree that describes what's going on. And in Racket, we use lots of signs other than parentheses to add some structure to our programs. So for example, you can look at where it says current custodian, and there's a left bracket and a right bracket. So many people, when they start using Racket from the Lisp world, they're blown away by the fact that we use like 2 other symbols, and it's very controversial, but nevertheless we do. And then you can also see that we make heavy use of dash to name things. Now, part of me, the other thing is that we use a lot of indentation. So this program, like, if I were to not have indentation, it would be like practically unreadable. It would be very difficult to understand. Now, when we look at other languages, like C, for instance, so here's a version of this program in something that's kind of like C. So, maybe it's sort of like C and kind of like Go. I don't know, just kind of like C-ish. So one of the things that we notice about this is that there's more. Oh, darn it. I'll have to turn that off. There's more implicit structure here. So what I mean by that is that, like, notice that, like, fun, accept, and handle, and handler, and listen, like, these things, they're like part of one unit in our mind, but they're not part of one sub thing inside of the syntax. So that means that behind the scenes, there has to be something that knows that fun has like these two things like inside of it, even though they're actually siblings. Now, that's something that doesn't really show up when you use S-expressions, because there would be a parenthesis right here and a parenthesis down here, and those things would tell us where the program was. Similarly, we see that there's other sorts of instances where siblings are associated, like here, and then there's also deeper structure when we have assignments like this. Now, something that's even more severe than this is a language that's like, that's like Haskell or Python that uses indentation as well. This program is like almost identical to the last program, except that I've added these colons right here and removed the braces. But now the idea is that the indentation here is forced. So something that I thought about a lot when we first started getting into the Rhombus project was how to produce something that is like S-expressions but has this structure right here. Now, there's obviously a gigantic amount of prior work on this where people try to define like indentation sensitive S-expressions or things like that, where basically the main idea of these, if I were to summarize them, is that the real language is S-expressions, and let's just make it convenient to write those S-expressions. And I wanted to think about this a little bit differently. So let's zero in on S-expressions for a little bit. So S-expressions, they kind of have this syntax where the body of your program is a list of forms, and then forms are either atoms, or there's a left parenthesis, and then a list of forms, and then a right parenthesis. And then there's also this one other syntax, which is that you can have a dot right here, and then a form after that. So this is like an extremely broad thing. And now, of course, in Racket, we do things a little bit differently, where we have a very complicated atom syntax, and we also have like reader macros and the add expression. But this is roughly what the surface syntax is. And of course, let me say one more thing, which is that we also allow different things for the left and right parentheses, namely brackets and braces, but they're purely on the surface. They don't actually, they're not relevant to the parse. And the way that we parse it is to something that's basically like this, where we have atom, and then we have syntax, cons, syntax, and syntax. And, really behind the scenes, syntax cons has a little bit more information, so it has stuff like where the source location information was. It does record what's called the parenthesis shape, which is whether it was a left parenthesis, or, well, whether it was a parenthesis, a bracket, or a brace. And there's other stuff too, but this is basically what the surface syntax is. Now, my first experiment with this I called C-exprs, and or Sexpurs, which has the same pronunciation but just a different way to write them down. And the idea here was to define a richer or more detailed parsing format. And so here's the parsing format that I came up with, and it's based on what C programs look like. So there are atoms, so there's things like numbers, symbols, etc. And then there are sequences of statements. And sequences of statements are like groups that occur inside of function bodies or on the top level. And then there are statements themselves, and statements themselves are things that are siblings of one another. So that would be like the fun definition, or like a return statement or something like that. And then inside of statements, there are also operations that are written in infix, and then there are applications where we record what the shape is, and we have the the function and then the argument. And then finally, because I wanted to deeply ingrain alternate syntaxes in text, I had the at form, which says that I'm calling this particular function, or well, here's like something that's at the front of the text, and then here's some text. And text can have a escape, which is the at form, or it can have a string, or it can have a sequence of texts. And so this right here was the format that I was going to target. And let's look at what the surface syntax was. It's a lot more detailed than S-expressions. So here's what the surface syntax I came up with was. Let me just move that a little bit. Okay. So the body of your program is a list of statements, a list of statements. That's what a body is. And then a statement is a list of expressions that's ended by a semicolon. And then we've got atoms. We have we have a special category of operators, which you can refer to alone, or they can be in prefix as a unary thing, binary, or you can use specific symbols, or you can have an application, and an application will have a shape of an opener and a shape of a closer. And then you can have braces for a body, and then grouping. And then braces for a body and grouping are invisible. Notice that they don't leave any residue in the syntax, so that means that you can't tell as a user whether you receive something with braces or with parentheses. So this is sort of like one of the goals that I had, that like parentheses would always be allowed. You could put them anywhere you wanted in your program. Then finally, there's an at form for text, and text just has escaping. You can embed more text, and then you can have any character. And so this right here is kind of the idea. Now, there's a lot more details that need to be specified, like what exactly are atoms, what are operators, what are the forms. But the idea is that like an example operator would be something like comma. And so since comma is an operator, that means that this function call form right here, you can have traditional function call notation because comma is just an operator. Similarly, you can have dot be an operator, and since dot's an operator, that means you can have, x dot y. And then since there are different kinds of shapes for openers, this means that you can have array notation, like array bracket x, be an example of a kind of application where we record what the kind of application it is. So let's look at a few example programs that are written in this form. So let me find a good place for my camera. Let's move it up here for now. Okay, so here's a little example. So you can have var x equals 3, and so this is a statement where there's var and then the operator equal x3. You can have function f, y, z, and then you have y plus x plus z, so you have a statement, which is fun. Then there's a paren shape where you have f and then the comma operator with y and z, and then some statements, and one statement inside of that, which is an operator with x, y, z. So the idea here is that the parsing is going to collect multiple occurrences of the same operator and combine them all together. And so we can also have things like let. Here's a little bit of a longer example. So this is for a function called timed thunk, where we get the before, we get the after, and notice that we use parentheses, but they don't show up in the program, and then we just end with answer sitting by itself. And then finally, I wanted to explore what a macro would look like, and so here's an example of a macro. So the example of a macro here is that we say mac timed, and then we're going to implicitly do a parse of what's outside. And one of the reasons that we want to have the braces form is so that we can have timed behave differently when it is in a statement position versus when it's in a call position. And so here we can call timed thunk and give it the thunk, or we can call timed and give it the e. And so the idea here is that the case can actually inspect. Notice that in the parse it has syntax statements on the left-hand side of an arrow, and over here it has syntax app on the left-hand side of an arrow. And so the idea is that each one of these is going to be an allowable thing that we can do. So I experimented with this, and we talked about it a bit. And I think that there's some pleasant things about it, but I wanted to push harder with the experiment. And rather than just having something that was, S expressions but C, I wanted to, go a little bit deeper. Here are some more examples. Functions, we could have like colon be its own operator, which allow us to get name arguments. And this is kind of like a proof case where we can say, dictionary key dot center dot x, and this parses into something. But as I said, this wasn't terse enough for me, and in particular, one of the things I felt is that it didn't rely enough on the indentation, which is something that I actually use when I program a lot, and so I wanted to try to incorporate that. And I also wanted to nail down an actual implementation because all of these parses are just like made up. It's just sort of a design document. So, oh yeah, and sorry, I keep sort of transitioning to the next thing, but I forgot that there's one more example. I just want to show you what using the text form would look like. And so my idea is that the text form is going to be really useful for embedding other programming languages as well as actual text. So here's like an example of including the data log. All right, now finally we can talk to the other thing. I was kind of rushing through C-exprs because I think they're cool and I do like C syntax a lot, but I spent a lot more time on Lexburs, and let me describe them a little bit. So the idea here is that we want to have something that is indentation sensitive, but indentation sensitive and completely structured, like S expressions are. And I had some really weird ideas that I wanted to apply. So let's just look at a little example program first. So here's a function that's called ksum. It's going to take k and L, and it's going to match on L if it's empty. Then we'll return 0. Otherwise, we'll see a cons of a and d, and we'll have a plus k times ksum kd. All right, so the main idea of Lexburs is that they have this concept called a line. And so the idea is that your program is a sequence of lines, and we have different ways that we can make lines have structure inside of them. So for example, right here we say that there's a line which has a fun, there's a function application of ksum, which is k and L. Notice that comma is not here. Comma is going to be like built in to the parser, so it's going to know about comma. And then notice that we have this colon right here, which turns into indent, and then inside of indent is the whole other thing. So this is sort of like the first big idea. So you know how when you're at like a shell script, or you can like write a line, and then you put a slash at the end, and this slash like cancels the new line and makes it so that the next line is actually part of the original line. The whole idea of Lexburs is to take that idea and run with it. So the idea is that a line right as it ends, whatever the last character is, that's if there's one before a new line, it's gonna change the interpretation about what comes next. And if you have a colon, then it's gonna mandate that you must indent line, and after you mandate that you indent, then the entire sequence of lines that come after that will have to be terminated by a blank line all by itself, and then all of that content will be inside of the indent. And that's why we get this indent with stuff inside of it. Now the next idea is that you can have a slash, and what the slash does is it continues on to the next line with a mandatory indent. So we must have an indent right here, but with these two characters because we ended in a slash. And then we can have a bar, and bar is going to be something similar, where it's going to say, okay, well when you have a bar, that means that we're going to have a sequence of bars that line up at exactly the right character, at exactly the same character as the previous bar. And then there's a line after them. And so this is an empty with a colon, and then that colon, we have a semicolon obviously as the way to blast away the rest of the line as a comment, and so on. Okay, let's look at another example. So here's that timed thunk thing again. Pretty much not a lot new here, except that we have the text form, which I'm very passionate about trying to add text everywhere, and so we just have braces, and then boom, right here's text with a escaping form of an at. Notice that it shows up as #text and #test escape. Okay. Now let's look at one last example of a macro. So the idea of the macro here is that macros are implicitly cased, which is why we use the bar. And then brackets are also going to be special. Brackets are basically going to quote a line. So by quoting this line, right here we say line with line _e inside of it, this is going to allow us to write macros that consume a line and do something to them. And then finally we have a quote form, which is going to quote something. Okay, so now let's look at some of the details of Lexburs. And I'm going to describe them very differently. I'm not going to describe them with like a grammar. I'm going to describe them with examples and stuff. So the idea is that Lexburs have new categories that are not like other languages. So there are what are called leaders, units, sequences, groups, lines, and text. So let's go through these. So leaders are things that are distinguished by whatever their first character is. So for instance, like an identifier is a leader because it doesn't start with a number or an operator. Numbers are leaders, they start with numbers. There are, characters, like individual characters which starts with like #/. And then there are embedded versions of all the other categories. So for instance, if you start with a parenthesis is going to open up a group, and a bracket is going to open up a line. So I don't want to get into all the details here. You can look at the proposal for this, but basically the idea is that leaders are sort of like the atoms in our language. Now the thing that's kind of interesting about leaders is that they have this category called units, which are leaders that are followed by another character. So for instance, when you have a leader followed by a left parenthesis, then this is going to open up a group that is like attached to the previous leader. That's going to be like a function call. And then if you have a dot at the end of a leader, then that is going to open up another unit, which is why we can get a sequence of dots all adjacent to one another. Now, the next concept is called a sequence, which is just a series of groups separated by commas. So this is where commas are built into the language. And then next, we've got groups. And groups are a series of units separated by spaces, and they're going to be parsed with infix notation. So notice that this is now mandating that infix notation can only appear in like certain positions. You can only appear when you're inside of a group, and to get a group, you've got to have, the only way to get a group is to be in a sequence. A sequence is a series of groups separated by commas, so commas are going to get you then, and then a left parenthesis is going to open up a group in function position, and also an embedded version of a leader is going to, a left parenthesis there is going to also open up a group. So notice that this language, this syntax is like extremely context sensitive. So a left parenthesis, you don't know what it means by itself. It could be inside of text, in which case it's just a left parenthesis. It could be to the right of a character symbol, which means it's like a quotation of that. It could be in a leader position, so it's going to open up a group, or it could be to the right of a leader, which means it's going to open up like a function call group. All right. So then we get lines, and I want to spend most of my time talking about lines. So lines are a series of units that are separated by spaces, and they always end in a follower. So let's look at a bunch of examples of line followers, because they're kind of the most interesting things. So there's just a new line. So a new line is going to completely separate them. So here are two different lines, foo, bar. So foo is a leader, which is also a unit. Bar is a leader, which is also a unit. Zig and zag are also that. And so this is one line, foo bar, and another line, zigzag. There are slashes, and basically what a slash does is it makes it so that this line continues on to the next line in the file, or in the stream, with a mandatory indentation. And by the way, in Lexburs, indentation is always exactly 2 space characters. So this right here is also 2 lines. These 2 programs are indistinguishable after parsing. You can't tell which one you got. Next we got and so and is like slash but does not have a mandatory indentation. So this is 2 lines, foo bar baz and zigzag. So again, you couldn't tell the difference between foo space bar space baz, foo slash bar slash, and then again baz, and foo and bar and baz. So the idea here is that when you are writing an Lexbur, you're like thinking, okay, well, how am I going to end this line? And any given line, you want to look back to the previous line and say, well, this is how it attaches to it. Okay, next we got colons, and what colons do is colons, the next line is a mandatory indent, and it's inside of it as 1 unit. And then here's something that's a little bit subtle, which is that the line afterwards is also part of it. So basically, when you have a colon, that means that you are going to parse a block of indented lines, and then once that indentation ends, you now continue the original line. So this is going to be parsed as if x less than y, and then an indent group, which is going to have a list of f and x, and then it's going to have else, and then it's going to have another indent group with g and y, and then because it ends, then now this group is over. Sorry, this line is over. So this is 1 line of a program that has 2 embedded lines which are indented. Next we got at, and so what at is going to do is it's going to have an indented text quotation, and it can have any number of lines, and it can escape with at. And like colon, the line that comes afterwards that is unindented is part of the original one. This is sort of like a rule of Lexburs. This language, by the way, is extremely carefully crafted with lots and lots of examples. All right, finally we got bars. And what bars do is they establish a sequence of lines which match up in their indentation and continue on to the next one. So notice that this one has to be in the exact same spot as that line. Text, it's delimited by braces, and I gotta escape. And that right there is Lexburs. Overall, I think that Lexburs are kind of cool. They have, I think, a relatively simple parsing algorithm, relatively simple to keep in your head. They produce what I think are pretty programs, but I would say that their main disadvantage, and same with the disadvantages of C-exprs, is that they don't push the limits of macrology. So what I mean by that is that one of the things that we're going to hear in a little bit about rhombus is that, or rather the sapling and shrubbery notation, is that they really go whole hog into the Honu style of having macros that consume their siblings rather than imposing a strict grouping. And I think that this is a very interesting thing that we've discovered as part of the the Rhombus Racket 2 project. So hopefully this has been interesting, and peace out.
Hey everyone. So time for questions for me.
I can feed you the questions if you'd like.
Yeah, great. Thanks.
I see there's a question in the doc, which is, so you showed an example with if else. So this is about L-exprs. What if it was when and when? So a when in place of the word if and else. And so how would, does the first when consume the second when in that case?
Yeah. So absolutely it would. And this is kind of one of those things that was a little bit ugly, where you really want if and else to be like one thing, but you also want it to look a particular way, where you want if and else to kind of share the same indentation. So because I started from wanting a program to look a certain way, like definitely like Lexburs are really oriented around, I wrote some example programs and I said, how can I parse that? How can I make whatever that is have an extremely rigid regular structure? And that's what kind of fell out this rule that after you do an indent, the next line counts as part of the first one. And when doesn't look good that way. And so what I would say, and like maybe your question is like, well, how do I get around it? You get around it with a blank line. So the idea is that, the indentation, what it does is it means that you don't have like closing indicators, right? With C-style programming, you have an opening brace and then a closing brace. And so it's obvious where something starts and ends. And indentation gets rid of that. But the next sort of thing is that syntaxes also have this situation where things like eat their siblings, like if, it's kind of a sibling to else, but it grabs it. And so rather than making it so that like if knows that it eats its sibling, you either have to make it so it's part of a larger group, which really gets us back to S-expression world, where you've got to delimit everything beforehand, or you have to come up with some other way of saying that like you always eat your sibling and a way to explicitly end it. And so Lexburs does that with a blank line, basically. So, whenever I wrote larger Lexbur programs, you would get this situation where you kind of like had to add like an extra blank line that you didn't really want to add, or you'd have to look for another way to do the indenting. So as an example, if you're going to have a sequence of whens, maybe you make it so that when actually, I don't know, uses like a bar and you list a whole bunch of different things that, okay, when this situation happens, you do it, when this situation happens. And the semantics of when is, it's not like con, where it will do the first one that matches and ignore the others. This when it really goes down the whole sequence. It's like a guarded block of stuff. So, this is kind of an example of why Lexburs are not as exciting as the other options. It's kind of a trade-off, right? Because it has the advantage of having a single rule that you always follow, but this rule isn't always nice. In contrast with what you're going to talk about, Matthew, which is saplings, which are going to approach this exact problem in a different way.
So inspired by things that you had in L-exprs. There's another question being typed. So the question is, if you have ABC and then backslash and the next line indented DEF, that's equivalent to putting it all on one line. Is it a convention whether to write it one way or the other? Is a style guide going to tell you whether to use one or the other? What was the intent?
Yeah. Let me rewind a little bit, which is that in Racket, we do not traditionally mandate that you use particular parentheses shapes in your macros, although it would technically be possible to do so. So for example, taking the cond macro, nothing tells you that the question and answer pairs have to use brackets, but every example that you'll see in the Racket documentation, in fact, uses brackets for that spot. And what you could do inside of syntax parse, for instance, would be very natural to do this, would be to add a constraint that would look at, I believe it's a syntax dash paren shape, or maybe it's a property. So you can look at that and you can say this had better be a bracket. And we don't do that, but part of, in my mind, the goal of dense syntax, where when I say dense syntax, that's kind of the way that I think about C and Haskell and whatnot, where there's a lot more in the syntax, which means that the job of the parser is going to do more, but that stuff is there for you, the reader, to look at. And so if, for instance, we could mandate that you always have to have brackets in this position in the cond, then you're sort of forcing the programmers to put in stuff for the next programmer. To continue with this a little bit, in Racket, it would be weird to make a macro that had its name and then just made you write a word halfway through it. You know what I mean? It just said oh, you just have to write else there. You could do a macro like that, but we don't do that. And if you were to ask a Racketeer why don't you do that? They would say something like, well, it's not needed. You don't do anything. You don't do anything.
People sometimes do that at first, but they learn not to do that.
Exactly. And this idea that it's not needed is you're talking like a compiler. You know what I mean? But the whole point is that humans need that thing. It's useful for them. So I wanted to try to figure out a way to add lots of these things. And so the idea with C-exprs is that everyone is going to mandate that it's a particular paren shape, because the different paren shapes are going to have a different interpretation in the main language. So bracket is just going to be a different thing. It's not going to be a normal parenthesis. Now, getting back to the original question of Lexburs, with indent and bar, those show up in the parse. So when your macro uses those, it's not just invisible. This idea that the notation is invisible, that's really what is underlying all of these alternative S-expression syntaxes, where they basically say, here's a really convenient way to produce something, but it doesn't show up, and therefore a macro can't enforce it. Therefore, the programmer community can't rely on that thing. And with Lexburs, with the slashes and ands, I felt that was more of a nod to people's different, styles of how they like writing stuff. And so I wanted those to be invisible. I didn't really write enough programs to decide if that was a good idea. But I think that, like I said, my inspiration is really Shell. And in Shell, the slash is invisible. You can't tell the difference. And so you're sort of adding that because you can't, you're offended by a really long line. And so I wanted to give a nod for people doing that, because I felt this line-oriented style, it would be very likely to get lines that are really long, and I am offended by long lines. So I wanted to have that be possible to be avoided invisibly.
Right. Someone is asking about the implementation of C-exprs and L-exprs.
Yeah. So for C-exprs, I did not do an implementation of that, mainly because I figured that it would be really obvious to do, except for like nailing down what exactly is the atom notation. That kind of wasn't the hard part in my mind. The hard part was like thinking through writing example programs, since I didn't do a parser for that. But then there's a parser and an implementation for Lexburs. And it you can give it programs and it parses them, and it's kind of fine. It just parses though, and it's not like tied to further things. So preview a little bit. Matthew's going to talk about his prototype, and his prototype is a real parser, but also it attaches to a particular, say, match macro that knows about its syntax. And so I didn't do that part of it. It was definitely because Lexburs had such a new way of thinking about what a program structure is. There, I felt like it was absolutely necessary to build a parser to make sure that it was really practical to deal with some of the issues that you might see. One of those issues, by the way, which I didn't really talk about in the talk, is that Lexburs need to really nail down what the operator syntax is and define which things are operators and how they get merged together. And so it has rules for defining those as fixed in the language. And I'll just sort of briefly say that, which is that rather than one of the goals that we want is infix notation, right? But having a really complicated infix notation that only deals with plus, multiply, times, and divide is really lame. You know what I mean? But so my sort of goal with that was to say, okay, well, I want to make it so that any random middle school kid, the thing that they write means what they think it means. So starting from that goal, what they mean is what they think it means. But I don't want to make it so that we get into the Haskell style line noise where there are thousands of operators with all sorts of weird things with weird precedences that are hard to internalize. So I basically said, after we go beyond the stuff that everyone already knows about, then you need to put parentheses everywhere. There is no precedence. You can use infix notation, but you got to manually parenthesize it and differentiate, the precedence yourself. And that decision is 100% inspired by my reading of Pirate, which is a language that Shuram worked on for a while.
I spent quite a bit of time with your Lexbur implementation, and we'll talk about how it inspired a response.
Cool.
Yeah, I think we are. I think we ran out of questions.
Good. Okay. Well, it's now your turn, Matthew.
Okay.
So let's make sure you can share your screen.
Right. All right. You can see that.
Yes, I can see it. And I'm going to turn off my video, but I'm going to leave on my mic in case I need to ask you a question if you don't notice.
All right. Ready, right?
Yes, go ahead.
All right. So shrubbery notation. So shrubbery rotation was it started out as a different thing, but the main idea, in contrast to what Jay said, and Jay foreshadowed this some, is the idea was a reader that only partially groups. So if you're going to write something like x plus y times z minus 10, the job of grouping that and deciding on precedence wouldn't be the job of the reader, as we understand it in this expression world, but instead would be deferred to a parser. But that doesn't mean that all decisions would be deferred to the parser. So the reader is still going to do useful things. It's still going to have a notion of grouping, if nothing else, parentheses, right? But as we'll see, more grouping than that. That is a kind of upper bound or a lower bound on the grouping, right? It says that in this example, for example, the parsing of times is not going to jump out of the parentheses and affect how G is treated, or G is not going to, if we're, we probably mean these to be lines, so it's not going to go back and change how F is treated in the parsing, right? And as Jay said, this is connected to some ideas we had tried out and that John Rafkin worked out in detail for his dissertation. And those ideas eventually carried directly over, although the parsing part there, the inforestation part, actually leads into what we build on top of shrubbery notation. But the notation was set up for that. So Jay also mentioned this intermediate point called sapling notation, which was line sensitive. It was after seeing Lexburs, and I tried taking seriously this idea that line breaks and could matter, and got into using colon and so on. So the idea is that when you write line breaks, that's really a strong indicator of your intended grouping. Maybe there's more grouping within the lines, but at least the lines as they're separated mean something about the grouping that you want. And also, as Jay said, what this does is it lets you avoid a lot of closing parens, closing brackets, and so on, all those closing delimiters. You get to leave off in a visually appealing way. And although I was happy with that, I decided, well, I'd better just try out whitespace sensitive, tab, indentation sensitive syntax to make sure I don't like it. It turns out that I did like it better. And it's because, well, of course, indentation is a strong indicator of your intended grouping, but then you can avoid even more closers. So here you can see that this G is less indented. It's not meant to be the body of the G anymore, but it's still inside fun F, so it's meant to be part of the enclosing function. Okay. So yes, it looks nice. Could we make it work out? That's where this all went. So the rest of this is meant to be a kind of tutorial or quick tour, but do interrupt me when you have questions. Again, either the chat in Gather or the document there, or Jay will interrupt me if you post something on YouTube. So let's talk about how these things parse, kind of in the same way that Jay described Lexburs. There's going to be fewer categories here. The main category is just a group. So to a first approximation, everything on a line is a group. So that's one group with 1, a plus, a 2, a times, and a 3 in it. And if you put things on different lines, then those are different groups. So 1 through 3, that's one group. And then 5 through 6, that is another group. You can, if you want to, separate two things in a line with a semicolon. So that creates two different groups here. Semicolon is not an operator here. It's part of the reader syntax, kind of at the same level that parentheses would be. So it's not that it's bound somehow to separate. It's that those things at the reader level are two different groups. A semicolon will never create an empty group, so you can throw an extra one at the end if you really want to. You can put as many in the middle if you want to. In Shrubbery, we ended up not doing this kind of thing very often, where there's some options about how you write things. But in the case of semicolons, it seems to be helpful and work out okay to just allow redundant semicolons.
By redundant, you mean they do not show up in the parse. That's what you meant.
They don't show up in the parse, and they don't form empty groups that would show up in the parse also, right? So these three semicolons, could be some groups between them, but there are no empty groups, and so they just go away. So then we get to the indentation part, and that's where colon comes in. Colon starts an indented block, and then the block has a sequence of groups. So here, log status, and then adding in parentheses, that's one group, and x plus 1 is another group. And the blue box around those, that's meant to be the block holding them. Now, the semicolon, the colon is kind of part of the block, although it also doesn't show up in the parse. But that block now is part of the group where the semicolon is. So the group is the function symbol, the F symbol, X in parentheses, and a block. And then that block has two things inside of it. The indentation for a block is 2 by convention, but you can put as much indentation as you want, and it doesn't matter. You can also start the block content on the same line if you want. And now here, it's whatever token is after the colon, whether it's on the same line or not, that determines the indentation for all the groups within that block. So that's why X really does have to be lined up under the L here. So that's one way of creating a block. Another way, and this is taken directly from Lexburs, is the idea that bar is another special thing, because bar looks really nice for things that branch, like if or cond or matches as in SML. So when you have a bar, that means this line that starts with the bar, that is more indented with respect to the previous line. We experimented with having colon bar combinations, but based on some community feedback and experiments, this is where we've landed. So bar means the current line is more indented than the one before it, and it's creating a block that continues that previous lines group. But then a new bar starts another alternative here, and to the right of each bar is another group. So it both creates a group in the enclosing thing, the first bar does, and then each bar creates groups on the inside. So we've got a group with error small here, a block with one group error small in it, and another block here with two groups, one that starts val and one that starts delta. Now I've left some space here in front of the bars, but we've decided that the standard indentation is to just put the bar directly under, but we also count bar as indented automatically by half a column, right? So that kind of corresponds to the fact that there's white space to the left of a bar, and this avoids some ambiguity. You can't line up a bar and a non-bar on the same column. So that makes sure that the space of things you write is smaller. Since we're starting a block after the bar, you could put it on the next line if you want to, just like you can with a block started with a colon. You can also, just like colon, its content can start on the same line. A bar can be on the same line as the group it's extending, and its block can be on the same line. And in this case, a bar ends that first one and starts a new alternative. The rules there are a little bit subtle, but in practice, they work out pretty intuitively. You can also have a mixture. So I've started the first bar, put the first bar continuing on the original line, and then the next line, the next alternative with its bar on the next line. But the first bar there determines the indentation wherever it is. Okay, and then the last place where you can use indentation is that if you start a line with an operator, then it can continue the previous line. This was a relatively late addition in the design based on experiments and feedback, and it seems to work well in combination with other refinements we made. So this is one big group that has 4 pluses and 5 identifiers in it. Here's another even better motivating example where bar by itself is an alternative, but bar greater than is just another operator. And so this is chaining things together like you might do with pipelines or generators. I think I'm forgetting the right word for these things, but
Threading methods.
Threading, thank you, threading, where you might thread through things. Okay, so those are the indentation rules. When you have parentheses and square brackets and curly braces, there are no new indentation rules. It just works the same on the inside. So I can have a function here with its body nested under there with conditionals, all as the argument to list. I guess there is a little bit of a new indentation rule, which is when you open a parentheses, you're going to have a closing parentheses. So the relative indentation of the content of the parentheses relative to the outside of the parentheses doesn't really matter. So you can start it wherever you want to. And the environment would indent like this. You could even indent it less than the list dot here, although that would look terrible and you should not do that. But the key point is that indentation doesn't somehow turn off just because you go inside of parentheses. The flip side of that is if you have an expression that's using indentation, you can just wrap parentheses around it if you need to. But one difference, there is another difference about parentheses, which is that you have to separate groups, not just by line breaks, but with a comma, and it doesn't have to be a line break. So comma is something like semicolon, except inside of parentheses, square brackets, and braces, except it's required. So here, because I've got a comma between x and minus y, that's 2 different groups. Even if I put them on the same line, the comma is separating the groups. If I left out the comma, then of course, that means one group, x minus y. If I left out the comma and put it on 2 different lines, then that's just an error, a reader error. So the intent here is that people mean to put commas to separate things inside of parentheses and square brackets and so on. And so let's make it required and take advantage of that being required. Unlike semicolon, you cannot have redundant commas, like you can't create an empty group using a comma. That would be a reader error. You are allowed to have a trailing comma though. This is a concession to when you have long lists of things and want to put it on multiple lines, and many languages allow this.
Can I ask a question about the comma?
Yeah.
For the function example with filter, if I wanted to have a second argument after that,
yeah,
where does the comma go? Does it go next to that 5?
Yep, goes right here. So you put a comma there, and then it'll be lined up under the the next argument.
Yeah, that's kind of neat that it can be at that last spot. It doesn't have to like be unindented from the fun.
Yeah, let's go try this out. So I'm going to switch into drracket now. If you want to play with this later, there's a package. It's not registered on the package server, but you can install it as a package from there. And that will give you a hashling shrubbery in drracket. So just to try out this example a little more, fun x, let's see, so we're doing map and fun x plus 1 onto a list 1, 2, 3, something like this. I wouldn't actually write map like that, of course, I would write it like this. But that's an example of the kind of things. So the environment is helping me out here with tabbing, and you can't see me hit the tab key, but that means it's a realistic indentation. And then when I run with ling shrubbery, you see the parsed form of that. So I'm going to go back and talk about that. Yeah, let's start with something simple. Again, let's go back to 1. So if I have the shrubbery 1, so what we're seeing down here at the bottom is the read result of 1 as an S expression. So 1 by itself is right here, but then it's on its own line, so it's in a group. And then I'm just using top to group everything at the top. So if I have 1 and 2, that's 2 different groups. So there's a group 1 and group 2. Whereas if I put 1 and 2 on the same line, then that's group 1, group 2 together. If I have an operator like plus, then that shows up in the parse as an up node here. Whereas if I have just a variable like x, just an identifier, it's not wrapped in any way. So in principle, identifiers and operators could overlap, but as we'll talk about in the lexing part, they don't. But there's a connection here to how do you deal with racket style identifiers in the shrubbery role. Let's try a block here. So if I say begin 1, 2 and run it, then you see that reads as a group that starts begin. This whole thing is going to be one group. We see one S expression here. It's got a begin token, but then we've got this colon with 2 more groups. So that is parses as block. And then we have the 2 groups. And I liked how Jay showed the grammar in his talk before. So it turns out the grammar of what shrubberies read at looks like this: top with some groups, groups with elements, an element's either an atom or an operator, or things with parentheses, braces, brackets, or it's a block, or it's an alts. I've showed you some of those. Let's do a few more. So if I do 1 in parentheses, that's a group that has parentheses that has 1 group in it with 1 in it. There is 2 groups in the parentheses. Change it to square brackets, then it's brackets instead of parens. If I change it to curly braces, it's curly braces, right? So we are distinguishing those different shapes of things. I see someone wonders about a parse error, so let's leave off curly brace there. So expected close curly brace. Let's say x colon. This turns out to be an error because empty blocks are not allowed, except with some other syntax I'll talk about later. Let's try alternatives. So what if we say if x, then y, else z? Actually, you'll notice that this is a valid indentation, and that was the first one that showed up just because I didn't have a bar there, but that's the other indentation here. And if we parse that, now we see if and x, and then a sequence of alternatives is in an alts where each alternative has its own block. Whereas if I leave the y out here, then of course I can get the empty block error message. Yeah, I think that's all I want to show here. That gives you some sense of how things parse out, and just a little bit of the environment support. So to fill in many of the pesky details, identifiers are just letters and numbers and underscore. Probably emojis should be in there, but we'll figure that out later. When I say alphanumeric, those are Unicode properties, right? And the usual rule that you don't start with a number. So these are all identifiers. Operators, unlike Jay, I was happy to just allow crazy UFOs like this as operators. but there are some interactions with things. So of course, you can't use all the characters that we've reserved, like parentheses and comma and semicolon, and I'll mention some of the others later. There are also some details with avoiding ambiguity with number syntax. So plus and minus, and also commas. These are a little bit restricted. And then we're also using colon and vertical bar. But most other things, Unicode symbols and punctuation, are allowed as operators. Numbers, compared to Racket, the number syntax is greatly simplified. You have exact integers, perhaps in hexadecimal form, but no octal, no binary. Floating point numbers in the usual way, or the 3 special floating point numbers, not a number, infinity or negative infinity. So we're using the scheme hash here as our escapes to do these one-off constants. If you need to get fancier identifiers or fancier numbers, like maybe XT steel is your favorite Racket number, which is an exact hexadecimal number that's a complex number using polar notation, you can do that by using hash curly brace. So hash curly brace gets you into the S expression world with all of the Racket S expression complexity and syntax. You can even misspell non-negative if you want to. So that's one of the key things.
Is that actually a Racket escape, or does it escape to lexemes like integers and identifiers?
It's an S expression escape. So there is a constraint on the S expression that it can't be list shaped. Otherwise, that creates ambiguity with the representation of parsed, but parse shrubberies. But otherwise, it's all of Racket S expressions, which you shouldn't use probably. I don't know, but we have that escape for now. Booleans, hash true, hash false. Probably nothing surprising there. Same for strings, except we fix up the minor detail of disallowing literal new lines like Racket allows. Keywords. For keywords, we use tilde. So we wanted something lighter weight than hash colon. This was a discussion among a number of people about what we should do here, and we settled on this, and it's worked out pretty well. So we do have keywords that are separate from identifiers or operators because they have all sorts of benefits for building syntactic constructs. And then at notation is just built right in, very much like it is in at expressions when you mix it with S expressions. There are a few differences that make it work better. But you can probably read this and guess what it means. The only thing that's really different here is that you can have multiple curly brace things in sequence because of the way this desugars into the underlying shrubbery. It makes sense and is useful to have that. Comments are basically C style, so line comments or slash star, ending with slash star, but they can nest unlike in C. And then there's also the analog to S expression comments. So what we're commenting out with hash slash slash is a group. So here, this is commenting out, remember the group starts fun fx, and then it's a block that's part of that group. So that whole group gets commented out. You can also use this group commenting form to comment out just one alternative in a sequence of alternatives, which is not exactly the same thing as commenting out a group, but very similar and works out similarly in the syntax. And you see here, we are commenting out the group that supplied the keyword argument base 2. This comma is separating groups, so we don't need to comment out the comma exactly. We're just commenting out the whole group there, and so it works in the natural way. It is possible to be explicit about your grouping if you want, and I'm using guillemots for that because it's not really meant for you to type directly. But there are a lot of situations where you just want to turn off whitespace sensitivity. I know some of you are thinking like all the time, but for those times that you really need to, for moving code around or something, the rule is you can use these opening brackets just after a colon or a bar, and then you close them off explicitly, and then you separate groups explicitly within them using a semicolon. So that thing parses the same as if you erased all of the noisy characters. This one does too, even though it's all smashed against the end. You could even put it all on one line. But that's sort of the natural form. And if it looks like this in the environment, you re-indent it, it'll of course go to this kind of shape. The drracket implementation, the plugin right now has a key binding for armoring. So you can, let's suppose we had this thing, but we're going to move it down here into some other place, right? And if I just copy it and paste it, then of course the indentation is going to get messed up. Maybe a way to deal with this is, first I have to make it valid, is armor it, right? And I didn't talk about colon guillemot, but that just groups the whole set of things together in case there's multiple ones. Then I can put it over here. Then I can make sure that my indentation is fixed up within, and then I can unarmor it. And this is part of the experiment. So that's the one big drawback I know about indentation sensitivity. And this is one way we're looking at how to deal with it. Also, just when you print shrubbery, the printer puts these things in so that it can just be on one line or not, depending. Right. So if you want to get into more of the details that I haven't talked about, you can go to Racket Rhombus brainstorming. I think, let's see, no. If you do that, you get to this GitHub site, and the README has pointers to these active proposals, as well as state of Rhombus and general discussion. Yeah, we jumped right into the Rhombus syntax experiments here, Jay and I did. We didn't give you any sort of overview. If you wanted an overview, that's a place where you can go. I will also mention that this examples link here are the examples that Sam mentioned earlier too. All right, so that is my whirlwind tour of shrubbery notation. Are there any other questions?
Right. There are two questions that are kind of like questions that fit at the end.
Okay.
So one is, so someone had a question about, does shrubbery support something like the and that was in my talk, where it like takes the next thing and like makes it so you don't need to indent it?
No, I can say that I experimented a lot with and to go along with vertical bar, and the end decided not to pursue it. So there is backslash, which has the usual backslash meaning. It just continues the line. If I try this, well, let's see, we got a different error message there. But, so you can see how this doesn't want to indent anymore because it's continuing that line, and then it's going to complain about this not being lined up there. But no, there's nothing like the end.
Okay. Another question is that, so Lisp has really like created a like its own continent of its own syntactic world, where it's very, if I'm making a new language, I can very cheaply implement S expressions, and you can just start using Emacs, and you'll be able to edit my weird language. And if I make a new language that, and it's very cheap, by the way, for me to make my language have S expressions. And if I make my language have something that's kind of like C, I'm not going to get a lot of support for free in other environments. It's going to be maybe a little bit easier to like get Vim to treat me like C, because I can like copy and paste some other thing and like add my keywords. But adding C, implementing C syntax is kind of hard. Do you see it as a goal or something that could be done in the future? Or what do you think about the problem of shrubbery being beyond Racket? Like, can we create a new category of syntax where people say, oh, I use shrubbery syntax in my language that, you know, I've implemented in JavaScript or Haskell, or, you know, there's just some other language that's not part of us that is using this new kind of idea, because this is a very new kind of syntax. It's not exactly like, oh, it's just Python, but it's different. What do you think about this problem?
Well, that certainly is the intent. And that's why this presentation and the Rhombus brainstorming and proposals was separated out the reader level notation from imposing an actual language or even a macro expander on top of it. So that's the intent, to do the S expression version of something where function calls look like function calls and arithmetic looks like arithmetic. How general that turns out to be, I don't know. Time will tell, perhaps. But that certainly is the intent.
Okay.
And part of it, just to make a little connection to S expressions, when you do S expressions in Emacs, the indentation that you get from them may or may not be what you had in mind, right?
Yeah.
And one of the goals here is to remove that question, like to have enough richness in the syntax where the indentation is purely driven by the reader level. So that you don't need binding information, or you don't need to customize that to your particular flavor of shrubberies as opposed to S expressions.
Maybe here's another way to ask this question. If you gave me C code and you said, implement a C parser, and it doesn't have to be like real actual C.
Okay, yeah, I didn't answer the other half, right? Which is, how easy is it to implement this parser? Yeah, it's nothing like S expressions. It's way trickier to build the parser. So it's more like C in that sense. Like, if it somehow succeeded, then what would happen would be there would just be the Emacs shrubbery parser that you could use as a component in your other thing. But it's nowhere near as easy as just consing up a new S expression parser real fast for your new embedded language.
Okay, cool. Okay, so another question is that dot notation. You never said, here's the time when we do something special with dot.
Right.
Is there no such thing? Like, is it not special? And why? How is it not special?
It's not special at the shrubbery level. It's just another operator like plus and minus. But we'll talk a lot about dot when we apply this notation to a language.
Okay. Someone asked, why the name shrubbery?
Well, it started as sapling was an idea. You don't have the full tree yet. You just have some of the structure, and it's going to grow into a full tree with parsing. And then, well, shrubbery is the Python style sapling. So that's how it became shrubbery.
Yeah, very good. Cool. Okay, so this is good. We'll now switch back to the hallway track, and we will, reconvene for the last session. In like right now, it's 3:36, so we'll reconvene at 4:30 in about an hour. And we'll do another walkthrough of the actual like language macro expander part of the current Rhombus experiment with Matthew again. And I hope that there will be lots and lots of details and questions for this, because this is like going to be quite a bit meatier, I think. Would you agree?
Yeah, and people might want to take a little bit of time in the break to go look at that Git repo. I mean, so I'm presenting a bunch of stuff here, and I did some implementation work, but I really got a lot of feedback and direction and redesign from other people involved in those discussions, and you can go see how some of this evolved if you want to.
Cool. All right, great. Okay, so the live stream will turn off now, and we'll connect back up in about an hour. Thanks, everyone.